Hi AP Chemistry. This is Chapter 11, the first video. This is going to cover sections 1 through 3. These are properties of solutions. Okay, so here's the definition of a solution. A solution is a homogeneous mixture of a solute and a solvent. Please remember that a solution can be any state of matter. It can be a liquid, it can be a gas, it can be a solid. The solute can be either the ionic salt, which is usually a solid, or the smaller amount of the solution. So if you're dealing with a liquid solution, the liquid that is in the smaller amount is the solute, and the liquid that is in the greater amount is the solvent. And usually our most popular solvent is water. When we are discussing mixtures, we're dealing with intermolecular forces. The intermolecular forces are those forces that are between molecules, usually responsible for physical properties, as opposed to Chapter 10, which were intramolecular forces, which were forces in the molecule, usually responsible for chemical properties. We're going to discuss solution composition, energies, and colligative properties, and I still might make those colligative properties a separate video. I think solution composition and the energies of a solution formation might be plenty to deal with. So colligative properties might be a different video. Alright, the dissolving process involves a consideration of the relative strength of three intermolecular attractive forces. And please remember that intermolecular means between like molecules. So you're going to be looking at the solute-solute intermolecular force that needs to be broken. You're going to be looking at the solvent-solvent intermolecular force that needs to be broken, and the solute-solvent intermolecular force that needs to be made. So again, think on it for a minute. In order for sodium chloride to dissolve in water, you need to break the sodium chloride intermolecular force and intramolecular force, separate the sodium from the chloride, then you have to separate the water molecules from each other and make room for the sodium and the chloride in between the water molecules. And then you have to have enough attraction between the sodium and the water molecules and the chloride and the water molecules for them to dissolve or surround the sodium and the chloride ions. So you're talking about solute-solute, inter, and intra with the example of sodium chloride. There is crossover, particularly around ionic salts. You are talking about the solute-solute attractive force, the solvent-solvent attractive force, and the solute-solvent attractive force. And if the solute-solvent attractive force is greater than the other two, you will get a solution. You will get something dissolving in water, because water is our most popular solvent. A solute will dissolve in a solvent, typically water, if the solute-solvent forces of attraction are great enough to overcome the solute-solute and solvent-solvent forces of attractions. So in other words, the sodium chloride attractive force and the water molecule to water molecule attractive force has to be less than the sodium ion attractive force to the water molecule. A solute will not dissolve if the solute-solvent forces of attraction are weaker than the individual solute-to-solute and solvent-to-solvent intermolecular attractions. So in other words, if you put sodium chloride in water and the sodium chloride likes the sodium chloride better than they like the water, you will not get dissolving. Generally, if all three of the intermolecular forces of attraction are roughly equal, the substances will be soluble in each other. So not only are you looking at a greater attraction for the water, but kind of like, yeah, all right, fine water, you're kind of looking at apathy almost. That's the way I put it in my head. Pretty equal. Sodium chloride says, sodium chloride or water, who am I more attracted to? It doesn't matter. Well, then you'll still get dissolution. You'll still get a dissolving substance. So greater than or equal to, you will get dissolving. Less than, you will not. All right, solution composition. These are a bunch of mathematical computations. Most of them you had first year chemistry. You have to remember the definitions of solute, solvent, and solution are. You also have to remember that the sum of the solute and the solvent will be equal to the total, which is the solution. All right, number one, molarity. You had it before, first year chemistry. Capital M is the symbol for molarity, not the units. Molarity is equal to moles of solute divided by liters of solution, and your units are moles per liter. Not only is that the definition of molarity, but it is also a three-variable computation. Moles of solute divided by liters of solution will give you the molarity or concentration of the solution. Literally, how many moles of the solute per 1 liter of solution do you have? Mass percent, real simple, mass of the solute, which is usually the smaller quantity, over mass of, again, the solution. The mass of the solution is the mass of the solute plus the mass of the solvent times 100. You've done percent before. Mole fraction, we had mole fraction in gas law chapter, pretty similar computation, but of course this time you're dealing with moles of a particular solute over total moles in solution, and again solution. So the first three, the denominator is all the solution, and the solution is the sum of the solvent and the solute. Keep the definitions straight, because notice the fourth computation, molality. Molality is another form of concentration for a solution. Its symbol is a little m, and its definition is different. It's moles of solute over kilograms of just the solvent. Solvent is not solution. Solvent is separate. It is a separate definition. Watch the definitions. And again, this guy is a computation with three variables. Units for molality will be moles per kilogram. Symbol for molality is a little m, because of course the big M is molarity, so it had to be a little m. This is three variables, just like molarity. Molality is calculated with moles of solute, kilograms of solvent. So three variables. Given any one of these three, you can find the other, just like molarity. Given any one of these three of molarity, you can find the other. All right, energies of solution formation. This is going to be strictly concept. So you're going to have to really think about this one. Like dissolves like. Driving forces in solution formation. Driving forces in solution formation. Number one, a decrease in energy when a solute or a solvent interact. An exothermic process. Again, here's our underlying principle. Less energy, the better. The less energy required to retain a solute-solvent interaction, a solute-solvent attractive force. The less energy required to retain that, the more expelled, the better it is. Increase in entropy when the solute-solvent interact. That means an increase in randomness. The entropy of the universe is increasing. Entropy is disorder, randomness. So these are your driving forces. Entropy is going to be discussed more later in the year. All right, I have a handout for you. We will discuss the handout in class. This is the preliminary work on it, though, and just think about it. The steps in solution formation. This is kind of like when we discussed the steps of forming an ionic solid. There are a multitude of enthalpy changes when you take a salt, a solid salt and place it in water. First off, you have to expand the solute, and in this example, let's say sodium chloride has to be expanded. You have to break that intramolecular force between the sodium ions and the chloride ions. And please remember, intra versus inter, there is crossover, particularly with ionic salts. So an intra/inter molecular force of an ionic compound, the sodium chloride, you have to split them in half. That is going to be an endothermic process. That change in enthalpy will be positive. Step number 2, you have to expand the solvent. Water molecules are highly polar. The intermolecular forces between water molecules are very strong because they are hydrogen bonding. Those intermolecular forces have to be broken. That's making room between water molecules so you can fit your sodium and your chloride ions in between the water molecules. That's going to require energy. So that's going to be a positive change in enthalpy. Step 1 is prepping the ionic salt, and I am using ionic salt as an example. So step 1 is prepping the ionic salt. Step 2 is prepping the water solvent. So step 1 and 2 are the prepping before you mix them together. Step 3, the solute and the solvent interact to form the solution. The interaction between the solute and the solvent should be an exothermic process. And the closer the solute and solvent get to each other when you dissolve them, remember, this is just a physical change. This is not chemical. Dissolving something in water is physical. If your solute can squeeze in nice and tight between the water molecules, then it's more exothermic. The entire sum of step 1, 2, and 3, the entire sum of step 1, 2, and 3 will be the enthalpy change of making a solution. Now think about it. Enthalpy change of making a solution. You actually came across this in the thermochemical chapter. Do you remember the lab where you put salts in water? One bag cooled and one bag warmed up. Alright, so the enthalpy change of the formation of a solution will be step 1, 2, and 3 added together. Step 1 is the expanding of the solute, prepping the solute. Step 2 is expanding the solvent, prepping the water. Step 3 is bringing them together. Step 2 and 3 they categorize as the enthalpy change of hydration, prepping your solvent and then bringing it together. That's just a definition. Alright, this is the handout I am going to give you when we discuss this in class. Again, enthalpy change number 1 is prepping your solute, expanding them apart, should be endothermic. Step 2 is expanding the solvent, separating your water molecules, should be endothermic. Step 3 is bringing them together, ideally exothermic. And then step 4 is the sum of the first 3. So this is a handout I'm going to give you. What I want you to know is like dissolves like. Polar solute, very large endothermic. Polar solvent, very large endothermic. Coming together, they're both polar, they're going to be attracted to each other, they're going to fit in nice and tight, you're going to have a very exothermic formation, you're going to have a very exothermic solute solvent attractive force. The sum of these 3 then, 2 large positives and a very large negative, you are going to get a very small number for the enthalpy change, which is a good thing. You're going to get almost 0. So that's a good thing. Probably why you can gargle with salt water and it does not burn or freeze your mouth, because the heat or enthalpy change of the formation of the salt going into the water is practically 0. And you get an outcome where a solution forms. So that's a good thing. That's a good one. A polar solvent and a nonpolar solute. If it's a nonpolar solute, the amount of energy required to separate them Non-polar solute means it's probably going to be London dispersion force or something like that. Not going to take a lot of energy to separate them. So very small endothermic. Polar solvent, which is going to be this one, is going to be, again, your water, and it's still going to be a large endothermic number. The solute will not have a large attraction for the polar solvent. So the solute will not fit in as well with the polar solvent, and you are going to have a small quantity of energy released. This is going to be a small exothermic. Remember, usually you want this to be exothermic. The more exothermic, the better. Well, this is very small. This is not going to be a tight fit between the solute and the solvent. So this is going to be a very small number. You're going to add these three up. A small endothermic and a large endothermic and a very small negative value is going to give you pretty much a large positive enthalpy change. That means this solution is not going to form. This is a bad thing. This one's good, this one's bad. It's not going to happen. And then the other two are just in the reverse orders. So it's really the first two that are good. It's really the first two I'm going to go through. The other two are pretty much the same thing. Nonpolar and nonpolar, that's going to work. Grant you this is going to be small, going to be around 0, but you're going to get a solution formation. Like dissolves like. All right, we're going to discuss this handout at greater length in class because it takes a little wrapping your head around. So look at it, think about it logically. Keep in mind, expanding the solute should be endothermic. Expanding the solvent should be endothermic. Bringing them together ideally should be exothermic, and the overall sum of the three should be approximately 0. So if you have a large endothermic, that means a polar solute and a polar solvent, your third energy, bringing them together, will be a large negative value. That means it's a good thing. Just what I said in the handout. That means like dissolves like. Polar and a polar. Highly exothermic, the interaction between the polar solute and the polar solvent. Highly exothermic. The sum of H1, H2, and H3 will be approximately 0 because you've got two big endos and one huge exo coming together to form almost 0 sum. If you have a small endothermic for your solute, but a big for your solvent, still using water, it's not going to be a tight fit. It's not going to be the right fit, so they're not going to release a lot of energy. It's going to retain a lot of energy to keep that solute and solvent together. That's a bad thing. This is not going to happen. You are going to end up having a very large endothermic sum of the three, and it's not right. It's not going to be good. If you have a nonpolar solute and a nonpolar solvent, you are going to have a very small endothermic energy needed to separate the solute. You're going to have a very small endothermic energy to separate the solvent. They're going to come together and they're going to release energy because that's going to be a pretty good fit. They're just kind of like, yeah, all right, you know what, I'm nonpolar, you're nonpolar, let's just do this thing, let's just go together. And they do it and it works. It's a small value for the sum of the three. And then finally the fourth one doesn't work. The fourth one's kind of like the second one. Look these over, make sure you write them down. They make sense if you think about it for a while, and we can discuss it more in class. And I'm definitely going to cut this into 2 videos. So this is the first video. Second one will be factors affecting solubility.